The first algorithm that will employ our de Miller-Lipton-Schwarz-Zippel lemma is the algorithm for checking matrix multiplication. So suppose that a friend of yours has computed a product of two matrices, A and B, and got some matrix C. But he or she is not quite sure about whether this computation was right or wrong. And so you are to check whether C is actually equal to A times B. Now you can do it, of course, by solving the problem from scratch. So you multiply these matrices and check whether the result is equal to C. Now, according to the current state of the art, you will need time approximately big O of n to the power 2.38. But it turns out that you do not really need to multiply the matrices yourself if you allow for tiny error in your check. And this is idea due to Freivalds. So assuming that A, B, and C are matrices containing elements of some field F, and they are all n by n matrices, and F can be a set of residues, modulo some prime, or rational numbers, or real numbers. But well, for real numbers, you need to be sure that you are able to do arithmetic on the computer with arbitrary precision involving real numbers. So we can freely assume that we have rationals, for instance. What we can now do? So let's now take a random column vector x, such that each of its components is taken at random from a finite set S. And let's compute the product A times B minus C times X. Now, to compute this product, we do not actually need to multiply matrices A and B, because we can write this as A times B times X and group it like this, and minus C times X. Now, a multiplication of an n by n matrix by a vector of dimensions n by 1 can be carried out in quadratic time. And then we get, again, a column vector, and the multiplication of A by this column vector takes, again, a quadratic time, if we assume that every arithmetic operation on components of vectors and matrices are done in constant time. And also, this guy can be performed in quadratic time. And finally, subtraction takes linear time, and thus the whole computation takes just quadratic time. And now we check if this guy is a non-zero vector. Now, if we have actually an equality here, then we answer that A times B is equal to C. If we have inequality here, we answer that A times B is not equal to C. So what we immediately see here is that this answer cannot be erroneous. So if this guy does not equal to 0, then of course A times B cannot be equal to C. And thus, if we answered like this is never wrong. But if we answered that A times B is equal to C, thus if we had this kind of equality, it doesn't necessarily mean that this matrix was an all-zero matrix. This might mean that we just, by coincidence, generated a solution to a system of linear equations with this non-zero matrix. But in terms of the components of the vector x, this guy, for a non-zero matrix, is just a linear polynomial p of x1 through xn, and the degree of this polynomial is equal to 1. And so now, let's compute the probability of an error, so that we have given our answer because we accidentally had an equality, but actually the matrix A times B does not equal to C. The probability of this event is equal to the probability that our polynomial P vanished on a random tuple of values that we have assigned to variables, whereas it was a not identical zero polynomial. And by the Miller-Lipton-Schwarz-Zippel lemma, we have this probability bounded by the degree of the polynomial over the cardinality of S. So thus, if we take the set S to be large enough, we can make this probability of error vanishingly small. And so we have a probabilistic algorithm which is able to check for whether two matrices are correctly multiplied. The negative answer is never erroneous, and the positive answer can be erroneous, but we can make the probability of this error vanishingly small. Well, this is of course a somewhat degenerate case of application of the Miller-Lipton-Schwarz-Zippel lemma, because we only deal here with polynomial of first degree, and we could possibly prove the same result without this lemma in the whole generality, but a bit later we'll apply it indeed to polynomials of higher degree.